Right, in this next chapter, we're going to look a little bit more into number theory. We're going to look at some interesting results and eventually get into some public key encryption results. So we begin with a simple but important theorem we call Fermat's little theorem, and it simply says that if P is a prime and the greatest common divisor of A and P is equal to 1, then A raised to the P minus 1 power is equal to 1 mod P. So first, I'll just point out, like with this statement here, if P is prime and the greatest common divisor of A and P is 1, that just means if P is prime and P does not divide A. We could rewrite that if we want. If you took this equation here that they give us, right, this sort of basic result, if you multiply both sides by A, then you get A to the P is equal to A mod P. So those are equivalent statements. We'll just make a couple of observations, a couple of examples to look at, that if A is 2 and P is equal to 5, then, and I'm going to cross this out because this equation is not true, but if A is 2 and P is equal to 5, what we get is that 2 raised to the 5 minus 1 power, this is 2 to the 4th, and we'll just observe 2 to the 4th, that's 16, and that is in fact equal to 1 mod 5. Now this next one says if A is 3 and P is equal to 5, we get, and then it gives us this example here, this equation, and we're looking at 3 to the 28th power. So just to show you kind of how we get there, if A is 3 and P is 5, then for sure 3 raised to the 5 minus 1 power is equal to 3 to the 4th, and that's 81, which is equal to 1 mod 5. Now we can use that result to get another result, and that's this one that we see right here. So 3 raised to the 28th power. 28 is a multiple of 4, right? That's how I'm actually going to use this. 28 is a multiple of 4, so 28 is 4 times 7. So I'm going to rewrite this as 3 to the 4 times 7. And when you're raising, or when you're multiplying in the exponent, that's equivalent to taking the exponential expression and raising that to a power. So 3 to the 4th all to the 7th power. Now 3 to the 4th all to the 7th power. 3 to the 4th we know is equal to 1 mod 5, so this is 1 to the 7th, which is 1. So we can use Fermat's little theorem here whenever the power is even just a multiple of P minus 1, which is what we saw here with 3 to the 28th power. Fermat's little theorem can be used to test if a number is composite. We should note that it cannot be used to determine if a number is prime. Now, if we get a result that is not equal to 1, right? If you know, just the order of this if-then statement just says if P is prime, then A to the P minus 1 is equal to 1 mod P. It does not go. It's not an if and only if. So if we got a result here, you know, with this equation that's highlighted in blue that was not equal to 1, we would be able to deduce that the number is not prime, that it is in fact composite. But if you got the result equal to 1, for every value A that you could plug in, it is not a guarantee that the number that you're testing, the one that we're calling P here, is a prime. For example, it can be shown that 2 raised to the 76th power is equal to 9 mod 77. And we're actually going to learn how to do that pretty shortly. We don't have to be able to raise 2 to the 76th power and find the whole value. We're going to look at an interesting technique really soon. So 2 raised to the 76th power is equal to 9 mod 77. 9 is not 1, and since 2 to the 76, and 76 is 77 minus 1, is not 1, then we can conclude that 77 is not prime. Now, it might seem kind of silly that we would use this theorem to conclude that 77 is not prime. We can factor it. We could see very clearly it's not prime. It's 7 times 11. However, this theorem could be used for numbers that are much, much bigger. And in fact, it has been used to show that huge numbers exist that are not prime, but we haven't even been able to find the factors yet. for example, this number right here has more than 5 million digits. 2 raised to the power 2 squared times 4 plus 1. And we know it to be composite, but no prime factors have been found. Again, I mentioned that we cannot use it to show that a number is prime. You might say, what if I keep getting 1 over and over and over again? Wouldn't that, result in us concluding that the number itself must be prime? And that's not true. In fact, there are numbers where we do get 1 for every possible value of a, but the number itself is not prime, and those are called Carmichael numbers. So here are some examples of Carmichael numbers. And what I mean by that is, if I take, for example, if I look at 561 and I take a to the 560, if I just let this value a run through lots of values, that as long as they don't divide 561, as long as the numbers itself have no common divisors with 561, and I let a run through all of these values and reduce mod 561, you'll see that you just keep getting 1 over and over and over again. But 561 is not prime. It is divisible by 3, I think. All right, so now we're going to look at a cool technique. We call this fast exponentiation, and it's a way that we can raise a number to a power, maybe a large power, without having to do a ton of multiplications. And what we need is to remember some rules of exponents. So for starters, if I am multiplying two numbers that have the same base, so a to the m times a to the n, then we can add the exponents. That's a to the m plus n. And if I raise a power to a power, then we can multiply those exponents. Now, we're going to first compute 3 to the 11th to see how this works. And we'll just note that if I were doing it by hand, just trying to find 3 to the 11th, I'd do 3 times 3 times 3 times 3, 11 factors of 3. So it would require 10 distinct multiplications, right, to finish this out. But what we're going to do first is rewrite 11, the exponent, as a sum of powers of 2. And there it is. It's kind of like writing 11 in binary, but instead of just putting the 1, or it's like writing it in binary, but the place values where we put a 1, we just actually put what that number would be as a base 10 number. So I'm writing it as a sum of powers of 2. And we're going to find 3 to the 11th, and we're going to do as few multiplications as possible. And here's how it works. We make a table with the first column is the total, then we look at our next factor, and then we decide, is it a desired factor? So here's what we mean by desired factor. We want 3 to the 11th, and this is 3 raised to the 1 plus 2 plus 8. So I'm adding in the exponent. So I can split this up as a multiplication. 3 to the 1st times 3 squared times 3 to the 8th, and these are our desired factors of 3 to the 11th. So we begin. The total column always starts with a 1. Our first factor is always what our base is, 3, and to the first. Regardless of what appears on your desired factors, we always start with base to the first power. So 3 to the first, which is, of course, 3. This is a desired factor. And if you answer yes to this question, that means we're going to change the total. And here's how we do it. I take what the total is currently, which is 1. I multiply it by the desired factor, which is 3. And I get 3, and there's my new total. Next, to get my next factor, what we do is square the result. square the previous factor. So this is 3 squared, which is 9. 3 squared is a desired factor. So we're going to change the total. I'm going to take what the total currently is, multiply it by the desired factor, and we get 27. Next, we get our new factor, always by squaring it. Now, I'm going to write this out in what seems like kind of a long way, but I'm just, it's going to help us develop a good habit to be in. So I'm squaring 3 squared. So when you square something raised to a power, we're going to multiply these exponents. I've got a power to a power. And we're always squaring. So when I square something, all I need to do is double the exponent. Right? And this does give us 81, which is exactly what we knew it was going to give us because we're squaring 9. This is not a desired factor, so the total holds at 27. Next, I'm going to get my new factor by squaring the one that came before. So my previous factor was 3 to the 4th. I'm going to square that. And when we square something, we're going to double the exponent. And I think I'll need the calculator for this. $6,561. This is a desired factor. So we're going to change the total. This is our last desired factor, so we're going to change the total one last time. $177,147. That was our last desired factor. That means that this new total is the result that we were looking for. So 3 to the 11th is equal to 177,147. So we'll note that the number of multiplications that was required, let's see, we needed 1, 2, 3, 4, 5, 6 multiplications instead of 10. We're going to find this technique to be useful for us for computing powers, for raising number to a power mod some other number. So we're going to take exactly what we were doing, only just look at the result mod, in this case, in example 6.3, we're going to look at it what it is mod 7. A lot of the time, people will call this modular exponentiation. It's still fast exponentiation. It's just in a scenario where we're reducing mod n, mod sum n. Now, what's really convenient about this is that if we're computing 5 to the 23rd power mod 7, for example, I could just reduce mod 7 at each step of the way. So my numbers will actually stay relatively small. I'm reducing mod 7. Every calculation, the result is going to be between, 0 and 6. So that helps make it a bit more efficient, or at least we don't end up swimming in a sea of digits. So we're going to compute 5 to the 23rd, and the first step is you write that power as a sum of powers of 2. So I always start by taking, just like when we found like binary representation, I'm just going to look for the biggest power of 2 first. So that'd be 16, 23 minus 16 is 7. So the next one would be 4. That gives us 20. We've got 3 left, so then 2 and 1. So there it is as a sum of powers of 2, and that means that 5 to the 23rd power is 5 to the 1st times 5 squared times 5 to the 4th times 5 to the 16th power. So these are our desired factors. All right, we're going to start filling in this table. The total always starts at 1. And as we go through this, we are going to reduce mod 7 at every step of the way. So that mod program that you put on your TI-83 or TI-84 will come in handy here. Our total is always 1. Our first factor is always our base to the first. So 5. This is a desired factor. So 1 times 5 is equal to 5. Our next one, 5 squared, we always square to get our next factor. This is 25. 25 mod 7 is 4. Right, 21 is a multiple of 7, so that's 4 more than a multiple of 7. 5 squared is a desired factor. So I'm going to take my total 5, multiply it by 4, I get 20. I want to reduce that mod 7. And if you reduce that mod 7, you should get 6. Next, my next factor I'm going to get by squaring. When you square something, you double the double the exponent. So my next factor is 5 to the 4th. And that, because I got it by squaring the previous one, that has to be the same as 4 squared. So I want to take 4 squared and reduce it mod 7. I get 2. 5 to the 4th is a desired factor, so that's yes. We're going to take 6, multiply it by our new factor, which is 2. I get 12, and if I reduce that mod 7, that's 5. Now I'm going to double the exponent again, because my new factor I'm going to square, so this will be 5 to the 8th. And I get it by squaring the previous result, so that's 2 squared, or 4. And 4 is already reduced mod 7, so I don't have to run that through the program or calculate it. This is not a desired factor. It's not on our list up here, so that means that our total holds at 5. And our next factor is 5 to the 16th, right? I'm squaring, so I'm going to double the denominator. That's what I get when I square 4, right? We're squaring everything. And 4 squared, we already found out, is 2 mod 7. This is a desired factor. In fact, it's our last desired factor. So I'm going to change the total one last time. 5 times 2 is 10. Reduce that mod 7 to get 3. And that's our result. 5 to the 23rd power is equal to 3 mod 7. Now, this technique is actually really useful because, we're working with, 5 to the 23rd power is quite large. And your calculator could compute 5 to the 23rd in general and express it as, in scientific notation, right? It's a really large number. It's so large, though, that the calculator doesn't know what its factors are. It's so large that it can't really, if you try to run it through the mod program, it just tells you that it's 0. Like, it's so large, it just says, it'll think everything's a factor of it. So, in fact, 5 to the 23rd is not 0 mod 7. So this fast exponentiation or modular exponentiation can help us out in ways that our calculator has a hard time doing. Let's do one more. We're going to compute 3 to the 50th power mod 10. We start by expressing 50 as a sum of powers of 2. So the highest power of 2 would be 32. That leaves us with 18, so 16. And then there's 2 left, so 2. So 32, 16, and 2. And that means that 3 to the 50th is 3 squared times 3 to the 16th times 3 to the 32nd. And these are the desired factors. Our total always starts at 1. We're taking everything mod 10. Mod 10 is easy to do because that just means we want the last digit, right? So if we're taking an integer, mod 10 just tells you what the last digit is. So our total starts at 10. Our first factor is 3 to the first. Always your base to the first power. So we get 3. That's already reduced mod 10. Not a desired factor, so our total holds at 1. Our next factor, we're just going to square things. So 3 squared, which is 9. That's already reduced mod 10. This is a desired factor. It's our first one. And our total changes. 1 times 9 is 9, and that's already reduced mod 10. We get our new factors by squaring the old one. So 3 squared, if I square that, double the exponent, 3 to the 4th, which is 9 squared, or 81. And that's 1, right? If you reduce something mod 10, you're just taking the last digit. So we get 1 here. 3 to the 4th is not a desired factor. So our total holds at 9. Now, before we go any further, we'll just note that our current factor is a 1. We get every new factor by squaring the one that just came before it. When you square 1, you'll get 1 every single time. So once we get a 1 here, all of the remaining factors will be 1, and the current total is the final total. So our next factors, 3 to the 8th, 3 to the 16th, 3 to the 32, these are all 1. And regardless of whether they're desired or not, right, this total is going to hold at 9. So we know that 3 to the 50th is equal to 9 mod 10. Now that's kind of a cool result. I mean, it's just interesting, I think, on its face, in that I take 3 to the 50th and I can pretty quickly tell you what the last digit of 3 to the 50th is going to be. And that's kind of interesting to me. All right, so we're going to switch gears a little bit. This will tie into our fast exponentiation. We're going to introduce a new function. We call it Euler's phi function. And for a positive integer n, phi of n is the number of positive integers less than n that are relatively prime to n. So look at all the integers from 1 up to n, or 1 up to n minus 1. How many of them are relatively prime to n? That's what phi of n is. So, for example, phi of 10. If I have the numbers from 1 to 9, the ones that are relatively prime to 10 are 1, 3, 5, no, not 5, 7, and 9, right? These other ones all share a factor with 10. So there are 1, 2, 3, 4 of them. That means phi of 10 is 4. It doesn't tell you, phi of 10 doesn't say what are they, what are the integers that are relatively prime. It just counts them, right? That's what this function does. Phi of 8 is also 4. And you can check this, but the integers less than 8 that are relatively prime will be 1, 3, 5, and 7. Phi of 11, take a second, think about what you think phi of 11 should be. Maybe you could point out the integers that will be relatively prime to it. You should find that phi of 11 is equal to 10. 11's prime, right? So all of the integers that are less than 11 should be relatively prime, are relatively prime to 11. So if you have any prime, phi of a prime is always going to be just p minus 1, right? So phi of 7 is 6, and phi of 23 will be 22, right? None of those integers are going to share any divisors with a prime. Phi of 15, let's see. So 15 is 3 times 5, which means if I'm looking for the integers that are relatively prime to 15, and bear with me, I'm going to just write them all out. I want to take out any multiples of 3 and any multiples of 5. And that leaves me with 1, 2, 4, 7, 8, 11, 13, 14, that's 1, 2, 3, 4, 5, 6, 8. So phi of 15 is 8. We're going to be able to find phi of very large numbers. And if we had to find phi of n, to find phi of n for all integers, if I had to go about it by listing all the integers and then trying to figure out what is relatively prime and what is not, it would be really cumbersome, time-consuming exercise. We have some useful results, though. The first one is a result that we already observed, but that if I have a prime number, p, phi of p is p minus 1. Right? All the integers less than it will be relatively prime. Next, if n and m are relatively prime, right? If n and m don't share any common divisors, then we can split up the phi function over multiplication. It's really important. This part is really important here of this result. We can only split it up if those factors don't share common divisors. And then if I have a prime, phi of a prime power, like p to the n, is p to the n minus p to the n minus 1. These results will allow us to compute phi of n pretty easily as long as we can factor n. So we're going to find phi of 1200. Right? And we're not going to do it by listing all the numbers and trying to figure out what is and is not relatively prime. We're going to start by factoring the number 1200. Make a little factor tree. And I want to go all the way down to primes. This is important. Right, so here are all of my primes. I got some 5s, I've got 3 2s, and I've got a 3. So the first thing I'm going to do is rewrite 1200 in its prime factorization. So I'm going to use the primes and their exponents. So I got 2 cubed times 3 times 5 squared. There's its prime factorization. Now, 2 cubed, oh, you know what? I missed a 2 here. Hold on. That's 2 to the 4th. Okay. 2 to the 4th times 3 times 5 squared. So 2 to the 4th n3, n5 squared, these are all relatively prime to each other. This is why we want to make sure we factor all the way down to primes, get the prime factorization, because then we can use that second result that says I can split up this function over multiplication. So I've got phi of 2 to the 4th times phi of 3 times phi of 5 squared. Now, each of these individual calculations now are covered by the three properties. So I've got this first one is phi of a prime power. Well, item 3 here, this third property says that phi of p to the n is p to the n minus p raised to the n minus 1. So if I'm using that on, 2 is prime, so if I'm using this on phi of 2 to the 4th, that third item tells me this will be 2 to the 4th minus 2 to the 3rd. Next I have phi of 3. That's a prime, so it's going to be p minus 1, or 2. And then 5 squared, phi of 5 squared is 5 squared minus 5 to the 1st. Alright, now we're going to just do some arithmetic. So 2 to the 4th, that's 16 minus 8 is 8, times 2 times 25 minus 5 is 20, and this gives us 320. So there is phi of 1200. And it did not require us to go through all the integers from 1 to 1199 and determine what's relatively prime to 1200. Again, this does not tell me what is relatively prime to 1200, just how many of those numbers are relatively prime. Let's do another one. Phi of 100. I'm going to start by just factoring 100, and I'm going to cheat here a little bit. We have the factor tree for 100 kind of embedded in our factor tree for 1200. So that's 5 squared, 2 squared. And because I wrote it as a prime factorization, now I can split up the phi function over multiplication. So phi of 5 squared times phi of 2 squared. I'm going to use that third item that says how I find phi of a prime power. So 5 squared minus 5 times 2 squared minus 2. 25 minus 5 is 20. 4 minus 2 is 2. So phi of 100 is 40. And let's do one more, phi of 40. So 40 is 4 times 10, 2 times 2, 2 times 5. So the prime factorization is 2 cubed times 5. I'm going to split up the phi function. Phi of 2 cubed times phi of 5. That is 2 cubed minus 2 squared times, now phi of 5, that's just a prime, it's not a prime power, so I can just go straight to that result, which is 4. You'll get the same thing if you use item 3, right? So here's like just a little, side quest or something. We'll just observe that we could still use item 3, that third property, because this is phi of 5 to the 1st, and this should be 5 to the 1st minus 5 to the 0, and anything to the 0 power is 1. So 5 minus 1 is 4. So really you could just use, say that items 2 and 3 are all we need, but item 1 is kind of low-hanging fruit, so I always include that in the list. 8 minus 4 is 4. 4 times 4 is 16. There's phi of 40. Okay, so we're going to find the Euler's phi function to be useful in some of this fast exponentiation work we've been doing. First, a result. This result is just a generalization of Fermat's little theorem. So Euler's theorem says that if a and n are relatively prime, so a and n can share no common divisors, then a raised to the phi of n is equal to 1 mod n. Fermat's little theorem is just Euler's theorem when n is prime. In example 6.7, like consider n equal to 10. Phi of 10 is equal to 4. That was one of the calculations, or I think we found phi of 10 by just listing all the values that were relatively prime to 10. Euler's theorem says that as long as a and doesn't have any common divisors with 10, so if a is not a multiple of 2 or 5, that a to the 4th power is equal to 1 mod 10. We can use this to deduce that 27 to the 4th power is 1 mod 10. We didn't have to compute 27 to the 4th power. We didn't even need to do fast exponentiation. We didn't have to set up that table. We just know that 27 does not have common factors with 10, and we needed to remember and observe that phi of 10 is equal to 4, right? So I basically, we were able to kind of just make this observation without having to do any calculations at all. So Euler's theorem can help us speed up the calculation of fast exponentiation. So 49 raised to the 320 power, that can be pretty tedious to calculate even with fast exponentiation, but 49 and 1200 are relatively prime to each other, and 320 is equal to phi of 1200. So that tells us that 49 to the 320 power mod 1200 is 1, doing no calculations at all. And even when Euler's theorem doesn't allow us to directly get to the result that we're looking for, it can be used to help us find efficiencies. So 7 raised to the 322 mod 1200. All right, so a couple things. One, if we're going to apply Euler's theorem, we need to check that it does apply. So note that the greatest common divisor of 7 and 1200 is equal to 1. They share no common divisors. So that means that we can apply Euler's theorem. And the next thing is we just want to make sure we're aware of the value of phi of 1200. We computed this on the last page. It's 320. Now our power is not 320, it's 322. But I'm going to use some rules of exponents and say that this is the same. I'm going to rewrite 320 as I'm going to rewrite 322 as 320 plus 2, and if I'm adding in the exponent, that means that's the same as multiplying. Now, Euler tells us that this is equal to 1. So now I'm applying Euler's theorem. Seven squared is 49, and that is already reduced to mod 1200. We didn't even have to do the table. Sometimes we'll still need to use that table to help us out, but Euler's theorem can kind of initially have the effect of initially just reducing the exponent that we're trying to work with, taking out all factors of phi of n. Let's do another one, 12 to the 30th power mod 29. So again, I'm going to check. 12 and 29 are relatively prime. That means that Euler's theorem can apply. And phi of 29 is equal to 28. So Euler here tells us that 12 raised to the 28th power is equal to 1 mod 29. I'm going to use that to make this calculation a lot easier. 12 to the 30th power. So 28 is sort of the magic number for me in that exponent. So this is 12 to the 28 plus 2, which is 12 to the 28 times 12 squared. mod 29. 12 to the 28, we know that's equal to 1. And 12 squared is 144. And 144 mod 29 is 28. Okay. Let's try one more. Let's say we want to know what are the last two digits of 3 raised to the 137 power. So if we want the last two digits, that means that we want to know what is this mod 100. So we want the value of 3 to the 137 power, mod 100. So first, there's a couple things I'm going to do. We're going to check and just make the observation that 3 and 100, they are relatively prime. That means that Euler's theorem can apply. Now, depending on what the exponent is, Euler's theorem isn't always super useful, but I think it will be in this case. Phi of 100, we computed that on the other page. That's equal to 40. And so Euler tells us that 3 raised to the 40th power is equal to 1 mod 100. Okay, so I'm going to take 3 to the 137. And what I want to do is just take out all the multiples of 40 from 137. So the highest multiple of 40 less than 137 is 120. And we'll just note that 137 is 40 times 3. That brings us to 120 plus 17. So this is 3 to the 40th all cubed times 3 to the 17th mod 100. That's what we're after. Now, just kind of, I want to make sure you stop and check and make sure that this line you're okay with. 40 was the magic number here because we're trying to find instances of 3 to the 40th power. So 120 is the highest power, 120 is the highest multiple of 40, and that's 40 times 3 plus 17. So if you check 40 times 3 plus 17, that is equal to 137. Because we're adding, that means that we can multiply, and 3 to the 40 times 3, if I'm multiplying in the exponent, that's the same as raising a power to a power. Now I'm going to apply Euler's theorem. 3 to the 40th is equal to 1 mod 100, so this is 1 cubed times 3 to the 17 mod 100, or 3 to the 17th power. Now that's still pretty high. Like I don't know off the top of my head what that is. But I can set up the fast exponentiation. And fast exponentiation with a power of 17 will be much more efficient than with a power of 137. So I'm going to set up my total. Here's my table. So the first column is for my total. Then I look at my factor. And then is this a desired factor? Okay, so 3 to the 17th. 17 is 16 plus 1. There it is, it's the sum of powers of 2. So 3 to the 17th is 3 to the 1st times 3 to the 16th. These are my desired factors. So my total always starts at 1. My first factor is 3 to the first, which is 3, and I'm all reducing mod 100 along the way for these two rows here. Three to the first is a desired factor, so 1 times 3 is 3, that's already reduced. My next factor is 3 squared, which is 9, already reduced. This is a no. In fact, my next desired factor is 3 to the 16th, so I'm going to have a bunch of rows here where my total sticks around at 3. So 3 to the 4th is 9 squared, which is 81. Already reduced mod 100. Not a desired factor, total holds at 3. Then 3 to the 8th, which is 81 squared. Mod 100 is 61. Not a desired factor, so again my total holds at 3. Then last, 3 to the 16th. There's my last desired factor. This is 61 squared. That's 21. This gets a yes, so I'm going to change my total. That is 63, already reduced mod 100. So now we know that the last two digits of 3 to the 137 are 63. Okay, so here's an observation I'd like to make. This fast exponentiation and Euler's theorem, these give us tools that allow us to figure out, they allow us to figure out a bunch of things, but like in this particular example, right, we're able to tell what the last two digits are. Last two digits means you want to know what it is, mod 100. If I want the last three digits, I want it mod 1,000. If I want the last four digits, I want it mod 10,000. They give us a way to examine a lens through which to look at really huge numbers and just say, what are the last two digits? Compare this to what we already know, what we've already learned about how we can use the common log function, the log base 10. That was a lens, with that tool, we were able to kind of, take a huge number, write it in scientific notation, and that allowed us to find what the first few digits are. So now we have these sort of two different ways to examine really large numbers. One way with logs gives us a way to figure out what the first few digits are. This way with fast exponentiation and Euler's theorem can help us figure out what the last few digits are. And so I just think that's an interesting observation. In the next section, we're going to see this technique helpful used in a type of public key encryption.